In this video, we'll continue to look at a few properties and simple operations that are associated with three space or three-dimensional space. And in this video, we're going to focus on distance, right? So you may recall, I'll go ahead and I'll state it, but let's say you're working in R2. So you're in R2, and let's say you have two ordered pairs, and they each represent points, right? So you have a x1 and a y1, and then you have x2 and y2. And yeah, let's say this is point 1, and let's say this is point 2. And what we would like to be able to do is to find the distance between them. Now, when you talk about the distance between two objects, you're essentially, what's often left out is the shortest, right? Because yeah, you can move along a curve and take a longer distance, or even on several like line segments to get from P1 to P2, but essentially we want to know how long is this, right? And so there are different ways you could say it. You could say, you could ask the question or phrase the question in this way: what is the distance between P1 and P2? Another way of thinking of distance is to think of it as the length. Now, since we're using like this line segment, which would be the shortest way to get from P1 to P2, you could phrase this question in another way. You could say, what is the length of line segment? And you might remember this notation for a line segment that has an initial, well, has one end point and another end point. To indicate that it's a line segment, you just put a line over these two letters with the subscripts, right? As opposed to putting like an arrow or anything like that. The arrow means a different type of object, which we will get to shortly, right? So you can, essentially figuring out what is the distance between these 2 points is equivalent to figuring out the length of that line segment. Well, how could we do this? Well, I am going to construct a right triangle. Right? So I'm going to construct a right triangle there, and I am going to identify the length of the base of this triangle and then the length of the height of the triangle. So the base of the triangle is essentially the distance between x2 and x1, because the base represents the change in the x value. So this distance here, I'm just going to take my larger x and subtract the smaller x, right? That way I don't have to worry about absolute values. Not that absolute values could be removed in a different way, but I think just taking the larger x and subtracting the smaller x, that will ensure that we're always going to have a positive length here. And then do something similar for the height of that triangle. Just take the difference between the y values. So take the larger y, which in this case is y1, and subtract the smaller y value, which is y2. So there you go. We have the base. We have this side and this side, and we have a right triangle. So the length, this line segment represents the hypotenuse of this triangle. So by Pythagoras, right? Now, so what is the notation that we use for distance? Well, there are lots of different things. We could simply just label that length d. So we could do that. Sometimes we might use d for distance, and then to indicate that it's the distance between these 2 points, you could do something like this. P1 comma P2. That's another way you can sort of indicate it. But the important thing now is because of Pythagoras, we now have a formula. And remember what Pythagoras says: if I want to find the hypotenuse, the length of the hypotenuse of a right triangle, square the lengths of the two shorter sides, add them together, and take your square root. So let's do it like this. So that means I'll do the x ones first. So I'll do x2 minus x1 squared, and then square the height of the triangle, which is your y1 minus y2, and then add them together, and then take your square root, right? And because these differences are being squared, this is where it actually doesn't matter if I do x2 minus x1 or x1 minus x2. So if you want it to be nice and symmetrical in a sense, you might restate it like this and say x1 minus x2 squared. It's the same, right? And then plus y1 minus y2 squared, right? And then that gives you the distance of these 2 points. And it turns out if we are now in R3, so in R3, so in fact, let me not make that too long, but let's say we're in R3 and we have our right hand orientation here. Let's say we have points, so let's say we have our P1. Now in R3 we need 3 coordinates, so I'm going to say x1, y1, z1, and then let's say over here I have P2, which is x2, y2, z2. If I want to find this distance, I can extend this Pythagorean result to 3 dimensions. Now, what we're going to do in a lot of those kind of intro ideas, we're not going to prove every single thing. We might prove something for R2 and then just extend it for R3, or vice versa. But in R3, if I want to find this distance, so now the distance d is equal to still a Pythagorean application. And what you do is, you're going to take the change in the x values and square, add to that the change in the y values squared, and then finally the change in the z values squared. And you'll see this sort of thing happen a lot, right? Essentially taking a known result from R2 and essentially extending it to R3 by then essentially following the same pattern, but now for the 3rd dimension, which in this case is the z dimension, right? So this is a formula for finding the distance between 2 points in R3, all right? So let's do a little example illustrating this and incorporating some of the ideas about coordinate planes and coordinate axes. So here's a little example. Right, so let A be the point, and so let's say it's 2, -3, 4. And then we're going to ask some distance questions about this point. So what is the distance from A to, and then we're going to go through like parts A, B, C, D of this question. So let's say so in part A, we want to find the distance from point A to the point 3, 8, -7. So what is that distance, right? Well, we can use our distance formula. So here's our answer here. So our distance is, and notice I'm not going to sketch these for this particular part. I'm not going to sketch it. I'm just going to identify. I'm going to say that here's x1, y1, z1, and then here is x2, y2, z2, and I'm going to take the difference between the x values. So I'm going to take 2 - 3 squared, and then I'm going to take negative 3 minus 8 squared, and then I'm also going to take 4 minus negative 7 squared, add those all together, and take the square root, right? So the idea of what we're doing here is, yes, there's a lot of geometry in terms of, you know, the spaces and the points and the lines and this stuff, but we're not relying on a picture to answer the question. We're going to rely on calculus, well, right now algebra, and then in the future calculus, right? So let's simplify and see what we get. So this is negative 1 squared, which is a positive 1, plus, then we have a negative 11 squared, which is a positive 121, and then we have a positive 11 squared, which again is 121. So 121 plus 121, that's 242, plus another one, so that's the square root of 243. And that's not a perfect square. I'm just going to leave it as the square root of 243. Now, if it's the distance, you know, you could always say it's this many units. If the question didn't mention any units, you could certainly leave it off. But this is the distance, right? So finding the distance from a point to another point, whether in 2 dimensions, 3 dimensions, doesn't make the problem any more difficult. But let's ask this question. What is the distance from point A, let's say, to the XZ plane? Right? So we know that this point is not along any of the coordinate axes nor any of the coordinate planes, because none of the coordinates is 0, right? So we want to know what is the shortest distance that I would have to go starting from point A to get to the XZ plane. Well, what we would have to do is figure out what is the closest point in the XZ plane to the point A. So let's make that observation, because once we can figure out what point in the XZ plane is closest to this point, then we can find the distance by using our distance formula. We just need to come up with that second point. So let's see. So in the XZ plane, the point closest to A is, well, think about it. In the XZ plane, what do we know for sure? We know that the Y value has to be 0, right? The Y value has to be 0. But X and Z can be anything. In order for the point that I'm coming up with to be closest to A, then I'd have to choose the same X and Z value of my point A, but then to force it to be in the XZ plane, I have to make the Y value 0. So it's this point, right? So so this point is closest to A and is a point in the XZ plane. So now to answer the question about the distance, use our distance formula and find the distance from this point to this point. Now when you look at it, you might be able to tell what the answer is, but I'm going to go through the calculations and then come back and say, hey, we should be able to just look at it and tell. So the distance in this case is, again now, so we're going to take the difference between the x values of each of the points, so that's 2 minus 2, and we're going to square those distances, and then negative 3 minus 0 squared, and then 4 minus 4 squared, and then I have to take the square root. right? So what happens here is, look, we end up with this really simple calculation. We have 0 squared plus -3 squared plus 0 squared. So that is the square root of 9, which is 3. And that's essentially the distance that you, since if you notice, there would be no change in the x value, there would be no change in the z value, but there would be a change of a positive 3 in the y value. So to get from this point to the xz plane, we would have to go 3 units in length, or a distance of 3 units, right? So a nice little question there. And let's do a part C. And let's say part C is to the, let's say to the y-axis. So to the y-axis. Right, so I want to get from the point to -3, 4 to the y-axis in the shortest possible distance. Well, let's see if we can write down the same sort of statement here. So along the y-axis, the point closest to A is, well, let's think about it. Along the y-axis, what do we know? We know that x has to be 0 and z has to be 0. But then if I want this point to be the closest point to this point, then the y value would have to be the same. If I change the y value, then it's not going to be the closest point, right? So this would have to be -3. So now I'm going to, again, use my distance formula to find the distance between 2, -3, 4, and the point 0, -3, 0, right? So here's our distance. So taking our difference, it's 2 minus 0 squared plus -3 minus -3 squared plus 4 minus 0 squared, and then take the square root of that because of good old Pythagoras. So what do we end up with? 4. This is 0. And then plus 16. So this is the square root of 20, and if you wanted to be all fancy and break this down, this will be 2 root 5 units, right? But just with a single formula of, to find a distance, we can now find the distance between a pair of 2 points, right? A pair of points, or a point and one of the coordinate planes, and a point and one of the coordinate axes. Going forward, we're going to come back to this idea of distance several times, but we're just, again, kind of setting the groundwork, getting used to using our distance formula. Now, one more thing I want to mention in this video is, so there are lots of different types of curves we could study, but we're going to start with the simplest type of curve, the circle, right? So let's take a look in R2. A circle is, and I'm not going to write this down. Again, this is not a full course in analytic geometry or constructive geometry, but we just need to make sure that we have a good understanding of these objects. But a circle is a set of points that is equidistant from a fixed point called the center, right? What does that mean? Well, it's a set of all points that are the same distance away from a fixed point that we call the center. And that fixed distance, that equidistant, that's the radius. And of course we have our center there. So if the center is at the point x0, y0, what we would like to be able to do is to use an equation to describe all the points that are the same fixed distance away from x0, y0. Right? So essentially we want to write down the equation of the circle. So here is the formula, and again you can easily use the distance formula to come up with this, but the equation of the circle centered at x0, y0, z0 with radius r with radius r, and again I'm going to assume that r is greater than 0. In a second I'll talk about what happens if the radius is 0 or what if the radius is negative, right? But the equation of the circle centered at, we're not in R3 yet, this is just R2, so centered at that ordered pair with that radius is, and you might remember this equation, it's x minus x0 squared plus y minus y0 squared is equal to, that doesn't look like a 2 at all, a 2, and then your r squared, right? So this is one standard way. It's an implicit equation, but it describes all the points that are on the boundary of the circle, right? So that's the circle. Now there are some things sometimes where we want to describe not just the points that are on the boundary of the circle, but all the points inside the circle. Whenever you're including not just the boundary points, but the points inside, so on and inside the circle, we refer to it as a disk. So it's like a coin now if you think about it, right? The equation of a closed disk centered at x0, y0 with radius r is, so if I want to include not just the points that are on the circle, right, that are the same distance away from the center, but all the other points inside that are closer, so what I would have to do is change this equal sign to a less than or equal to. So what that's saying is all the points that are no further than r units away from the center would be described by this inequality. So the difference between just talking about the circle, which represents the boundary, as opposed to everything that's inside it, which is what we would describe as a closed disk. Now, the reason why we say closed is because the boundary is included. So the sketch for this is basically, let me use a different color here. So it's like this. That's our center. That's our radius. But now we're including everything here, right? So it's a circular object, but it's not just the boundary itself, but everything inside. There is the concept of an open disk, and that's when we remove the boundary points. So, an open disk. So an open disk with the same center and radius is defined by just removing the equal sign now and then it's x minus x0 squared plus y minus y0 squared, and then that's strictly less than r squared. Right? And the reason why the r is squared here is, notice I'm not writing the square root sign. So essentially we're getting rid of the square root and using this as the standard equation. So this is the an equation for the open disk that is centered at x0, y0 with radius r. And in terms of the sketch for that, the boundary would not be included. There's our center. That distance is still r, but we're just removing the boundary and then looking at all the points strictly that are within less than r units of the center. Right? So that's the two-dimensional setup. Well, what is the three-dimensional analog of a circle? Well, think about it. It would be a sphere. Right? So all of these ideas now translate over to a sphere in R3. Right? So what I will do, I will sketch 3 of these. Well, actually, I'll just do 2. I'll do the closed ball. That's what it would be called, versus the sphere. So the sphere would look like this, and it starts like that, and then just give it, just do something like that, going around, right? And then this point right here would be the center, and then that distance there would be the radius. So let me just say that this is a sphere, and the center again would be at a specific point. So at a point we're going to use x0, y0, z0. The radius is still going to be some number r greater than 0. And then here is the standard equation. Right? And it looks exactly like this, but it has a third term on the left-hand side of the equation, or in this case, of the equation. And when we include the points inside, it will be an inequality. So here's the equation. So it's x minus x0 squared plus y minus y0 squared plus z minus z0 squared, and then that's equal to r squared, right? And now when so the three-dimensional analog of a closed disk is a ball, a closed ball. So think of the difference between, let me draw this, and then we have this there, but then also everything inside, right? So it's like solid all the way through. So that's still your center, that's still your radius, but think of it as a ping pong ball, which is hollow, versus a golf ball, which is solid all the way through. So we call this a closed ball, and it's defined by an inequality. So the center and the radius is the same. It's just that now we're including not just the points on the surface, but everything inside. And that's why we need an inequality for that. And it's exactly what we have here, but just change that to less than or equal to. So we have x minus x0 squared plus y minus y0, not z yet, y0 squared plus z minus z0 squared. That's equal to r, or less than or equal to r squared, right? And there we go. So, why do we do, why are we looking at circles or and spheres? Well, those are some of the simplest, most important geometric objects that are out there. There are other ones that we're going to look at. We're going to look at lines. We're going to look at planes more generally, but we're starting with these relatively basic ones. And also, in order to define the equation of a circle or a sphere, all you need is that simple distance formula. So that's why we tend to do these all together. All right, so I think it's probably a good idea for us to end with an example. And let's do an example that involves a sphere. And what I'm going to do is a question where we have to find the center and radius of a sphere, right? That's what we're going to find, but it's not going to be written in this nice standard form where you have like a perfect square here, a perfect square here, and a perfect square here. Instead, it's going to be expanded like this. So it's going to look x squared plus y squared plus z squared minus 2x minus 4y plus 8z plus 17 is equal to 0. All right? So we're being told that this equation represents a sphere, but it's not in the standard form, right? So this is not in standard form. So we can't just look and tell what the center is and what the radius is. What we have to do is to convert this to the standard form. And the trick from algebra that we need is to complete the square. But we have to do it 3 times. We have to do it for the x, for the y, and for the z terms. So here is the process. The first thing we're going to do is to take the constant term and move it to the right, right? So that's, we're going to move the plus 17 to the right and make it a negative 17. And while we do that, let's group all the terms that have an x and a y and a z. So we have x squared minus 2x. I'm going to group that, and I'm going to kind of leave a space there, and then do the same thing for the y's. So we have y squared and then minus 4y, and then plus the z's, we have z squared plus 8z, and again I'm going to leave a little gap there, and then equals, and then on this side I have a negative 17. So what we would like to do, because we want the left hand side to look like this, so we want to convert this into a perfect square. But what it's missing is, it's missing that constant that would make it a perfect square. So what we have to do, and this is the process that I'm going to write over here, hopefully you remembered how to complete the square. So completing the square, and we're going to have to do it in x, in y, and z. So completing the square in x, y, and z gives this. Now, the general procedure, and again, I'm not going to go through the full completing the square process, but once you have your trinomial where the leading coefficient is 1, which we have in for all 3 of these, the leading coefficient is 1, you take a half of the coefficient of x and square it. That's what the constant has to be, right? So in other words, I am going to take the half of negative 2, which is negative 1, and then I'm going to square it, and I'm going to write that in as so that becomes a plus 1, right? And then I'm going to do the same for this one. I'm going to take a half of this coefficient, that's a negative 2, and then I'm going to square it, and I'm going to put that constant again right here, right? And then finally do the same thing for the z. I'm going to take a half of the z coefficient, so half of 8 is 4, and square it, that's going to be 16. So we're going to do our plus 16 there. And now we're guaranteed that all three of these, oh, I didn't square this one. Now I can say all three of these are perfect squares. But look at this. I had an equation, so I can't just add a 1, a 4, and a 16 on the left-hand side and not do anything on the right-hand side. So I have to balance it. I have to add the 1 and the 4 and the 16 there as well. All right. So let's see. So now this is a perfect square, and this factors as x minus 1 squared. This factors as y minus 2 squared, and this factors as z plus 4 squared. Right? So that's what we did there. Our trick was completing the square. And on this side, what do we have? We have negative 17 plus 21, so that's a positive 4. So now I'm going to write this so that it looks exactly like our standard definition for a sphere. I have my x minus 1 squared plus y minus 2 squared plus z, and I'm going to write it as minus negative 4 squared, and then this 4 can be written as 2 squared. Why am I doing this? Well, it means that, let me use this, it means that this is x0, this is y0, this is z0, and those numbers represent the coordinates of the center of the sphere, and this number here that's being squared is my radius. So now we can identify the center and the radius of the sphere. So the center is the point 1, 2, negative 4, and the radius is 2. I'll just say r equals 2, right? So if you're given the point and the radius, it's easy to write down the equation. But sometimes if the equation is given to you in a slightly different form, you'd have to convert it over to that standard form before identifying the center and the radius. So a nice little example to end this video, and it involves an important process of completing the square. And again, this I would say is one of the simpler types of examples of completing the square, and we'll if needed, we'll work on the more challenging ones together. So until then, I'll see you in the next video.